In the previous episode, we talked about the history of quantum mechanics and showed that the particles in microvolt can behave as waves. In this episode, we'll discuss the concept of matter waves and some conclusion that it leads to. I begin with one of the fundamental and important experiments in quantum mechanics, which is the so-called double-slit experiment. In that experiment, one firstly shoots an electron beam on the wall with a single slit on it. That leads to some Gaussian-like distribution of the electron's position in the screen located behind the wall. If you shoot the same beam through the second slit, you'll obtain the same Gaussian-like peak. Shooting through two open slits obviously should result in two separate peaks, since electron can go through either one or another slit. However, this is the old classical and incorrect view. The real experiment results in complex interference picture with several peaks, including one in the center. What is the reason of that? You can argue that there is some interaction between electrons in the beam, leading to interference picture. But if you shoot electrons sequentially, one by one, you obtain the same picture, like electrons mysteriously interact with itself and behave as a wave. The wave of the matter, obeying the same laws as light or acoustic waves. In this section, we will discuss the matter waves that can describe the strange behavior of the particles in microvolt. Consider the propagation of matter waves in a homogeneous medium. The simplest type of the wave is a plain monochromatic wave. It represents a vibration of wavelength equal to 2p divided by k, traveling in the direction of the wave vector k with constant velocity. The velocity considered here is the velocity of propagation of planes of equal phases, or phase velocity, which is equal to omega divided by k. The frequency may depend upon the length of the wave vector. This dependence is called dispersion law. By Planck hypothesis, each frequency omega corresponds to the energy E of the particle. So, we can associate the wave with uniform motion of the energy E directed parallel to k. By examining this wave, we are going to relate wave vector k to momentum p of the particle. To do that, we associate the particle with a wave of limited extension. The monochromatic wave evidently does not satisfy this condition, since it is uniform in a whole space. One may realize it by superposition of plane waves with different wave vectors. So, let's form a wave packet out of waves with wave vector close to some k. Namely, f of k prime have a sharp peak in some k and equal to 0 in a remaining region. Let's denote the phase of the wave by phi. The wave packet is the integral of the product of a function f of k prime exhibiting a pronounced peak in region of the wave vector k with some extension delta k, and oscillating function exponent of I phi. If the number of oscillation is in this region is large, the contribution to the integral from the different portion of the region interfere destructively, and psi remains negligible. The largest absolute value of psi are obtained when the phase phi remains practically constant in delta k. So d phi over dk is approximately equal to 0. Roughly speaking, the only significant values of psi are those for which exponent of I phi carries out only one or a fraction of one oscillation, namely k times d phi over dk, approximately equal to or less than 0. Since d phi over dk is equal to x minus t times d omega over dk, the inequality adopts the following form. This wave packet surrounds the center defined by the condition d phi over dk equal to 0, which leads to linear dependence of the coordinate on the time. You can see that this is the equation of motion of the particle traveling with the velocity vg equal to d omega over dk. It is called the group velocity of the wave. It is this velocity that must be identified with the wave packet velocity. From the other side, from the classical point of view, we know that particle velocity can be expressed as energy derivative with respect to the momentum, v equal to dE over dP. Comparing these two equations and recalling the relationship between energy and frequency, we can find the de Broglie relationship, P equal to h bar times k. This procedure can be easily generalized to the three-dimensional case. Let's take a step back and rewrite the boundary of wave packet. It obeys the following inequality: delta k times delta x is approximately equal to 1, or delta p times delta x approximately equal to h bar. You can see that more precisely you define the momentum of the particle, more blurred is the wave packet, and more uncertain is the particle location. More strictly, it is deformulated in the following form: delta p times delta x greater or equal to h bar halved. That is the fundamental law called Heisenberg inequality. Now we know the properties of the wave packet of the matter wave. Let's think about the laws they obey. Obviously, it cannot be all Newton's laws, since wave packet, as we saw, has no exactly determined coordinate and momentum, which are demanded for classical equations. However, we can use the energy conservation law, which is the fundamental for both theories. So, the energy equal to sum of the kinetic and potential part. Here is the wave packet written in terms of energy and momentum due to the relationship we have established before. Differentiating it with respect to time multiplies the amplitude by factor minus I times E divided by h bar. Or if we differentiate the wave packet with respect to time and multiply it by factor IH, we gain the energy. Differentiating it with respect to time multiplies the amplitude by factor minus I times E divided by h bar. Or if we differentiate the wave packet with respect to time and multiply it by factor IH, we will gain the energy. Differentiating the wave packet with respect to coordinate and multiplying it by factor IH bar, we get a factor P, which is the momentum. To multiply the wave packet by some function of the coordinate g of x, we have just to multiply it. So, we can write the following correspondence. Time derivative corresponds to the energy coordinate coordinate derivative corresponds to the momentum. Second coordinate derivative corresponds to the momentum square. Comparing this with energy conservation law, we get the following correspondence of the energy and some differential equation. So you can see that considering the wave packet allows us to multiple conclusions. We can define the relationship between the momentum and wavelength, find the fundamental limitations of momentum and position determination, find the easy procedure of calculating of wave momentum, and define the laws that govern the particle behavior in quantum mechanics. In the next episode, we'll discuss the quantum mechanical way of describing the particles, namely, we'll introduce the concept of the wave function and discuss its properties.